Welcome to this coding walkthrough. In this video, we'll tackle LeetCode problem number 1046, last stone weight. This problem focuses on simulating a process to reduce a collection of stones until one or none remain. We'll explore its requirements and break down the solution step by step. Let's dive in. The problem we're solving is called last stone weight. You are given an array of integers called stones, where each element represents the weight of a particular stone. The task is to simulate a game where, in each turn, you pick the two heaviest stones and smash them together. There are two possible outcomes from this smash. If the weights of the two stones are equal, both stones are destroyed. However, if the weights are different, the lighter stone is destroyed, and the heavier stone's weight is reduced by the weight of the lighter one. The game continues until there is at most one stone left. Your goal is to return the weight of the last remaining stone. If no stones are left, the result should be 0. The constraints specify that the number of stones will be between 1 and 30, and the weight of each stone will be between 1 and 1000. The output is a single integer representing the weight of the last stone, or 0 if no stones remain. Let's look at an example to understand the problem better. Suppose the input array is stones equals 2, 7, 4, 1, 8, 1. The output in this case is 1. Here's how the process unfolds. First, we select the two heaviest stones, which are 8 and 7. Smashing them gives a new stone of weight 8, 7 equals 1, leaving us with the stones 2, 4, 1, 1, 1. Next, we pick the two heaviest stones again, which are 4 and 2. Smashing them results in a new stone of weight 4, 2 equals 2, leaving 2, 1, 1, 1. Then, we pick the heaviest stones 2 and 1. Smashing them gives a new stone of weight 2, 1 equals 1, and the remaining stones are 1, 1, 1. Now we continue processing the stones. From the remaining stones, 1, 1, 1, we select the two heaviest stones, which are 1 and 1. Since these two stones have the same weight, smashing them destroys both stones, leaving just one stone, 1. At this point, there is only one stone left, and its weight is 1. So, the output for this example is 1. Another simple example is when the input array is stones equals 1. Here, there is only one stone, so no smashing is required. The last remaining stone has a weight of 1, which is the output. Let's look at another example to see how all stones can be destroyed. If the input is stones equals 10, 4, 6, 10, 2, the output is 0. Here's the step-by-step process. First, we select the two heaviest stones, 10 and 10. Smashing them destroys both stones, leaving 4, 6, 2. Next, the heaviest stones are 6 and 4. Smashing them results in a new stone of weight 6, 4 equals 2, leaving 2, 2. Finally, we smash the two remaining stones 2 and 2, which destroys both of them. Now, there are no stones left, so the output is 0. This demonstrates that it's possible for all stones to be eliminated entirely. To wrap up, let's review the constraints and some edge cases. The number of stones, stones.length, will always be between 1 and 30, and the weight of each stone will be between 1 and 1000. For edge cases, consider a scenario where there's only one stone in the array, like stones equals 5. In this case, the result is simply the weight of that stone, which is 5. Another edge case is when all stones are eventually destroyed, as we saw earlier with stones equals 4, 4, 2, 2, where the output is 0. Finally, it's important to ensure that your solution can handle the maximum constraints, such as when there are 30 stones, each with a weight of 1000. These considerations will help ensure your solution is robust and handles all possible inputs correctly. To solve this problem, we need to repeatedly identify and smash the two heaviest stones. A brute force approach to achieve this would involve sorting the stones array on every turn. By sorting in descending order, the two largest stones become the first two elements, making them easy to access. Once identified, we smash the two stones by subtracting their weights, and if there's a remaining weight, we insert it back into the array. We continue this process until only one or no stones are left. However, sorting the array repeatedly is inefficient. Sorting takes n log n time, and if there are up to n turns, the overall complexity becomes n squared log n. This approach does more work than necessary because we don't need to fully sort the array each time, we only need the two largest stones. This inefficiency leads us to consider an optimized strategy using a max heap. A max heap provides a much more efficient way to manage and retrieve the largest elements. The key idea is that a heap allows us to extract the maximum element in just O log n time, which is significantly faster than sorting an entire array. To implement this, we first convert the stones array into a max heap. Since Python's heap library only supports min heaps, we simulate a max heap by pushing the negative of each stone's weight into the heap. Then, while there are more than one stone remaining, we repeatedly extract the two largest stones, represented as the two smallest negative values, smash them, and if there's a remainder, push the result back into the heap. At the end, the heap will either be empty or contain one stone, which will be the result. This approach is not only faster but also more efficient. Building the heap takes O, n, and each extraction and insertion takes O, log n. With up to n iterations, the total time complexity becomes O, n log n, which is a significant improvement over the brute force method. For this problem, we chose the optimized max heap approach because it delivers the best balance of efficiency and simplicity. The key insight was recognizing that accessing the two heaviest stones repeatedly is a perfect use case for the heap's logarithmic extraction and insertion operations. This eliminates unnecessary sorting, reducing the overall time complexity to O, n log n. While the heap requires O, n, additional space, this trade-off is negligible given the performance benefits. Another consideration is implementation complexity, but Python's heap library simplifies heap operations, making this approach straightforward to implement. Compared to the brute force method, the heap-based solution minimizes redundant work and focuses only on the largest elements, resulting in a faster and cleaner solution. It effectively balances efficiency, clarity, and practicality, making it the preferred strategy for this problem. The problem we are solving involves repeatedly smashing the two heaviest stones in a list until only one or no stones remain. When two stones are smashed, the smaller one is destroyed, and the larger one is reduced by the smaller stone's weight. If the two stones are of equal weight, both are destroyed. Our goal is to determine the weight of the last remaining stone, or return 0 if all stones are destroyed. To solve this, we can start with a brute force approach that relies on sorting the stones. The intuition here is that sorting the array in descending order will always place the two largest stones at the beginning, making it straightforward to pick and smash them. The first step of the algorithm involves input validation. We check if the stones array is empty and return 0 immediately if it is. Additionally, we ensure that all elements in the stones array are positive integers, as negative or zero weights would not make sense in this context. The next step in the brute force approach involves an iterative process. While there is more than one stone in the array, we repeatedly sort the array in descending order. This ensures that the two heaviest stones are always at the start. We then extract these two stones and compute the result of smashing them. If the two stones are equal in weight, both are destroyed and removed from the array. Otherwise, the larger stone is replaced by the weight difference, and the smaller one is removed. Once the iterations are complete, we check the state of the array. If there is one stone left, we return its weight. If the array is empty, we return 0. This process, while simple, is not the most efficient due to the repeated sorting at each step. Analyzing this approach further, we see that sorting the array in each iteration has a time complexity of O, n log n, where n is the number of stones. Since this sorting is repeated until one or no stones remain, the worst-case total complexity is O, n squared log n. This happens when we process the stones one by one. A key inefficiency here is the redundant sorting, or resorting the entire array from scratch in every iteration. Using a more suitable data structure, like a heap, can significantly reduce this overhead. Additionally, we need to account for edge cases. For instance, if there's only one stone in the array, we can immediately return its weight. If all stones are of equal weight, they will eventually be destroyed, leaving the array empty. And, of course, if the array is empty to begin with, we simply return 0. The brute force approach uses an array to manage the list of stones, but it's worth noting that a max heap could be used to optimize the process by retrieving the two heaviest stones in logarithmic time. Breaking down the key operations, we start with sorting, which ensures that the two heaviest stones are always at the beginning of the array. While this operation is straightforward, it is computationally expensive with a time complexity of O, n log n. The next operation is smashing the stones, which is just a subtraction to calculate the new weight of the larger stone, making it very efficient at 1. Finally, updating the array, removing and inserting elements, can take up to n, in the worst case due to the shifting of elements. To better understand this process, let's walk through an example. Suppose we have the stones equals 2, 7, 4, 1, 8, 1. First, we sort them to get 8, 7, 4, 2, 1, 1. Smashing the two largest stones, 8 and 7, leaves us with a new stone of weight 1. The updated array becomes 4, 2, 1, 1, 1. Sorting again gives 4, 2, 1, 1, 1, and smashing 4 and 2 leaves a new stone of weight 2. This process continues until only one or no stones remain. After following this process, the final result in our example is 1. However, while the brute force approach is simple and intuitive, it is not optimal for larger inputs. To improve efficiency, we can replace sorting with a max heap. A max heap allows us to retrieve the two heaviest stones in logarithmic time, reducing the overall time complexity from n squared log n to n log n. Furthermore, using an in-place sorting algorithm can help minimize memory usage. In terms of complexity analysis, the brute force approach has a time complexity of n squared log n, due to the repeated sorting, while the space complexity is n, for storing the array. Although this method works for smaller input sizes, for larger datasets, an optimized solution using heaps is highly recommended to achieve better performance. This Python solution for the last stone weight problem efficiently uses a max heap approach via Python's Heap module, which natively supports min heaps. To simulate a max heap, we store all stone weights as negatives, e.g., -7 for a weight of 7. This allows the smallest element in the heap, most negative, to represent the heaviest stone. First, the input list stones is converted to a list of negative values. The heap.heapify function is then used to transform this list into a valid heap structure. The heap ensures that the minimum element, most negative, is always at the root, which corresponds to the heaviest stone. Inside the while loop, which runs as long as there are at least 2 stones in the heap, the 2 largest stones are retrieved using heap.heappop. These values are negated to restore their original positive weights. If the 2 stones have unequal weights, the difference is calculated and pushed back into the heap as a negative value. If the 2 stones are of equal weight, both are destroyed, and nothing is pushed back. Finally, when no more than 1 stone remains in the heap, the loop terminates. If the heap is not empty, the single remaining stone's weight is returned, negated back to positive. If the heap is empty, the result is 0, indicating no stones remain. This approach is efficient, with the heap operations ensuring a time complexity of n log n, where n is the number of stones. The use of a heap ensures that we avoid the overhead of repeatedly sorting the list, as would occur in a simpler but less efficient approach. This is the Java implementation for LeetCode problem number 1046, last stone weight. The logic mirrors the Python solution, using a max heap to handle the stones. In Java, the priority queue is configured to behave like a max heap by providing a custom comparator. The last stone weight method performs the same iterative simulation, comparing the 2 heaviest stones, and returning the weight of the last remaining stone, or 0 if none remain. Key differences include Java's explicit type declarations and the use of the priority queue class instead of Python's heap library. To solve this problem, we start by converting the given list of stone weights into negative values. This allows us to use Python's Heap module, which provides a min heap by default, to simulate the behavior of a max heap. For the input 2, 7, 4, 1, 8, 1, the stone weights become -2, -7, -4, -1, -8, -1. Next, we apply the heapify operation, which rearranges the list into a valid heap structure. The heap now looks like -8, -7, -4, -1, -2, -1, with the smallest element, representing the largest original weight, at the root. In the first iteration, we extract the 2 heaviest stones, which are 8 and 7. Smashing these results in a new stone of weight 1, which we push back into the heap, leaving the heap as -4, -2, -1, -1, -1. Now, in the second iteration, the 2 heaviest stones are 4 and 2. Smashing these gives a new stone of weight 2, which we add back to the heap, resulting in -2, -1, -1, -1. In the third iteration, we extract 2 and 1 as the heaviest stones. Smashing them leaves a new stone of weight 1, and the heap becomes -1, -1, -1. Finally, in the fourth iteration, we take the 2 heaviest stones, which are both 1. When these are smashed, the result is 0. Since the result is 0, it is not added back to the heap, leaving us with just 1 stone in the heap, -1. At this point, only 1 stone remains, so the output is the absolute value of this last stone, which is 1. In this example, all the stones have the same weight. The input is 4, 4, 4, 4, which we first convert to negative values, resulting in -4, -4, -4, -4. After heapifying, the structure remains the same as -4, -4, -4, -4, because all elements are equal. In the first iteration, we take the 2 heaviest stones, both of weight 4. Smashing them produces a new stone of weight 0. Since the weight is 0, we do not add it back to the heap. This leaves the heap as -4, -4. Next, in the second iteration, we again take the 2 heaviest stones, which are both 4. Smashing these results in another stone of weight 0. As before, we do not push 0 back into the heap, leaving the heap empty. With no stones remaining, the heap is now in its final state. This means the output for this example is 0, as no stones are left after all iterations. In this scenario, we have only 1 stone to begin with, so no smashing is required. The input, 5, is first converted to negative values, resulting in -5. After applying the heapify operation, the heap remains -5. Since there's only 1 stone in the heap, no iterations are needed. The final state of the heap is -5, and the output is the absolute value of the remaining stone, which is 5. The time complexity of this solution is largely influenced by the operations performed on the heap. First, we need to construct the heap. This involves converting all the elements in the stones list to negative values, which takes n time since we process each element individually. Next, we use Python's heap.heapify function to build the heap, which also takes n time because it uses Floyd's in-place heap construction algorithm. So, the total time for the initial heap construction is n. After that, we process the stones in a while loop. In each iteration, we remove the 2 largest stones using heap pop, and if there's a resulting stone, we insert it back using heap push. Both of these operations run in log k time, where k is the number of elements in the heap. The loop can run up to n1 times in the worst case, resulting in a total time complexity of n1 * log n, which simplifies to n log n. Now, when we combine the time complexity of the heap construction, which is n, with the time complexity of the while loop, which is n log n, the overall time complexity becomes n plus n log n. Since n log n dominates n, the total time complexity is n log n. As for space complexity, the primary factor is the space required to store the heap. The heap is constructed directly from the input list, and its size is at most n, which results in n space. Additionally, we use auxiliary space for temporary variables such as heaviest and second_heaviest, which only require 1 space. However, the list comprehension that converts the stones to negative values temporarily creates a new list of size n, which adds another n space. Therefore, the space complexity includes n for the heap and n for auxiliary operations, but since these are not cumulative, the total space complexity remains n. Combining all considerations, the total space complexity of this solution is n. Comparing this heap-based approach to a naive brute force method highlights the optimization. A brute force solution would involve repeatedly sorting the list to find the 2 largest stones, resolving their collision, and then sorting again. Sorting the list takes n log n, and doing this repeatedly for up to n1 iterations results in a total time complexity of n squared log n. This is significantly less efficient than the heap-based approach. By using a priority queue, we avoid repeatedly sorting the list and instead perform log n operations for each removal or insertion. This optimization reduces the overall time complexity to n log n, making the heap-based solution much more suitable for larger datasets. Analyzing the best, average, and worst cases of this solution provides additional insight. In the best-case scenario, all stones have the same weight, and only one iteration of the while loop is required. Here, the time complexity is just O, n, for heap construction. In the average case, where the stones have random weights, the while loop runs multiple iterations, leading to a time complexity of O, n log n. In the worst-case scenario, where all stones have unique weights, the while loop runs for n1 iterations, and the time complexity remains O, n log n. From a mathematical perspective, the heap construction time of O, n, is derived from Floyd's algorithm, which efficiently builds the heap in linear time. The O, log n, complexity of heap pop and heap push is due to the binary tree structure of the heap, where operations adjust along the height of the tree, which is log n. Since the while loop performs these operations up to n1 times, the total complexity is O, n log n, confirming the efficiency of this approach. When solving this problem, it's easy to fall into a few common pitfalls. One frequent mistake is sorting the array on every iteration in order to find the two heaviest stones. While this approach seems straightforward, it results in a time complexity of O, n squared asterisk log n, which is highly inefficient for large inputs. Instead, optimized data structures like heaps can achieve much better performance. Another common issue is not properly handling edge cases, such as when there are fewer than 2 stones or when all stones have the same weight. Missing these scenarios can lead to runtime errors or incorrect results. Lastly, it's important to fully understand the problem requirements. For example, the goal is to return the weight of the single remaining stone, not the total weight of all leftover stones. Misinterpreting this can lead to output that doesn't meet the problem's specifications. Another mistake to watch out for is using a min heap directly to store stone weights. Since min heaps prioritize the smallest elements, they don't align naturally with the goal of repeatedly finding the 2 largest stones. Trying to invert values or reorder elements within a min heap adds unnecessary complexity. Additionally, overcomplicating the solution with redundant operations, such as repeatedly copying arrays or performing unnecessary checks, can increase time complexity and make the code harder to read. While it's important to ensure correctness, simplicity and efficiency are key in crafting a well-optimized solution. In interviews, it's crucial to demonstrate a clear thought process and a focus on optimization. Start by discussing a brute force solution, such as sorting, and then explain how heaps provide a more efficient approach. Mentioning edge cases up front, like an empty array, a single stone, or all stones with the same weight, shows that you're thorough and attentive to detail. Be ready to discuss trade-offs, such as how heap-based solutions compare to sorting in terms of time and space complexity. Also, ensure you're comfortable implementing heaps in your chosen programming language. For example, in Python, understanding the heap library is essential, as it defaults to a min heap, requiring you to use negative values to simulate a max heap. Finally, if you use a priority queue approach, explain how it directly addresses the problem's requirement to repeatedly extract the 2 largest elements. This problem shares similarities with several other heap-related challenges, which can help you deepen your understanding of the topic. For instance, LeetCode 215, kth largest element in an array, also involves efficiently finding the largest elements using heaps. The current problem, last stone weight, is essentially a direct implementation of the given scenario. LeetCode 973, k closest points to origin, uses heap-based solutions to efficiently select specific points, while LeetCode 295, find median from datastream, focuses on managing heaps dynamically to extract specific elements over time. Exploring these related problems can enhance your grasp of diverse heap applications. There are several approaches to solving this problem, each with its own trade-offs. A sorting-based approach involves repeatedly sorting the array to find and process the 2 heaviest stones. While this method is simple to implement, its O, n squared asterisk log n, time complexity makes it inefficient for large inputs. A heap-based approach, on the other hand, is recommended for its efficiency. By using a max heap, you can quickly extract the 2 largest elements and push the difference back into the heap if it's non-zero. This approach has a time complexity of O, n asterisk log n, and is significantly faster, though it requires slightly more complex code. Alternatively, if the range of stone weights is small and bounded, a bucket sort or counting approach can be used. This method involves counting occurrences of each weight and simulating the stone smashing process. With a time complexity of O, n plus W, where W is the range of weights, it's highly efficient for small ranges but impractical for larger or unbounded ones. Great job! You've made it to the end of this problem walkthrough. We covered the last stone weight problem and discussed its brute force solution. Remember the importance of choosing the right data structures for efficiency. Keep practicing, and don't forget to like and subscribe for more coding tutorials. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!